Hey everyone, am I audible? Like, can you hear me?
Yes, sir.
Yes, sir.
Good afternoon, sir.
Good afternoon, everyone. So, yeah, we are really sorry for yesterday. So, I guess yesterday was like in the IIT Madras, there was some issue. So, we were not able to start the session. So, so today, what we'll do, we'll just go through the fifth week, whatever the activity practices, and then we'll solve some problems. And then tomorrow again we'll meet. Like we can have one more session. Okay, is that fine for everyone?
So
Because
today we will do week 5 or week 6?
today we'll do whatever we have planned for yesterday, and for week 6 we'll meet tomorrow again. So tomorrow, till now, the session has not been updated, but I already informed for one extra session tomorrow. So your deadline is, I guess, 12th of June, right? For the week 5 and 6.
Yes, sir.
So for regarding the deadline also, I talked, but I didn't got the reply till now. So I thought I just asked them to extend the date till 15th, but I didn't got any response till now. If I'll get any, I'll just ask them to announce everyone. Okay. Till now, it's 12th June only, but I have just mailed them regarding the extension because week 5 is pretty difficult. Other than that, from next week, not next week, next to next, from week 7, all the contents are pretty simple and you won't face any issue in that. Only this linear algebra part was a bit difficult, and everybody generally have the issue in this. Like even me have a issue. Like everyone, all the students also generally face the issue in 5th week and 6th week. Okay, uh, so that's why we have thought of one extra session. Like whatever the session got cancelled yesterday. And if you want some extra session also, we can have, like we have the resources, we have the people, we can have one like extra sessions also till week 7. Yeah, after week 7, everything is pretty simple. So you won't be needing any sessions and also. Okay. The voice is clear, right?
Yes, sir. Yes, sir.
Okay.
Is it possible to make it a little more clear? Because
Okay. So I need to switch off my fan. Then okay, I'll do that.
I think it's a bit low.
It's low.
Yeah, sir, it is not about your fan. It is about your mic.
Is it fine now? I'll just increase the voice of the laptop. It's fine now?
Yes, sir.
Or is it the same?
It was same, sir.
It is somewhat the same. It's still,
Kind of
it is
same.
audible, but it is somewhat
Oh,
the same.
okay, okay. So that AirPod is not working. What can I do? I'll then.
So it is okay, sir. Like we could hear you,
Yeah,
but
Okay. So
clarity
what
was
is?
missing.
Yeah, yeah. Go.
No, no, sir, continue. It was okay.
So what I was asking. So for tomorrow's session, what's the suitable time when the like you would be having some other sessions also, right? So what is the time that you're free? Like last term when our professor Arun took the session, we were having some other sessions also. So it's better you can give me some time so that I'll put the session at the same time tomorrow. So what's the free time when you're not having any other sessions?
after 6, it will good, sir.
Okay, 6 to 8, right?
no, 6 we have DBMS.
Wait, somebody
Yeah,
joined
yes, sir,
me.
DBMS.
DBMS is there.
For 4
So
to 6
what?
also, we have app also, sir.
So what
2
about
to,
the same time as today?
8 to
Yeah,
10 is very late, I guess. Not
yeah.
late, but yeah, 8 to 10 I used to take the session in stats 2, I guess. But Ram should be available at that time because Ram generally takes the session in Python also. So he should be available, I guess, tomorrow. 2 to 4 is fine, right? 2 to 4
Yes, sir.
tomorrow.
Yes.
2 to 4 are little difficult, sir.
Oh, okay. See that.
8 to 10, I do not have any problem. Anything after 6, no issue. 8 to 10 will be fine for me.
But, the 6 to 8, it's like we are not free. Other than that, we are free. Like 6 to 8 is occupied. Other than that, everything is free tomorrow. So yeah, 4 to 6 is also fine. I'll just ask Ram once.
4 to 6 we have also session like FDEV 1.
Oh, okay, then 2 to 4, I guess it's fine. 2 to 4, nobody is having any sessions. Right?
Yes, sir.
There
2
is no
to 4.
session. There is no session at least.
Yeah, there's no session at least, right?
Yes, sir. Yes, sir.
Yes, sir.
So where is the somebody is asking refresher week? We don't have a refresher week in this MLF. But what we did earlier, maybe some of you would be not from you. Last batch, this whatever you are reading this 5th week and you'll read in the 6th week was totally occupied in 1 week. So last year it was very difficult for the student. Now we have splitted that in 3 weeks, 5, 6, and 7. So whatever the content earlier, last term, it was in the 5th week. We have split it to 5th and 6th. Half of the went to the 6th week. So we've just split it so that during the 5th week there is a quiz also, so we'll be having a less burden at that time. But will be, but what we did, we have just merged up the 10th and 11th week. But those are stats part, probability and statistics. Those you already have read in stats 2 and stats 1. So I don't think so there will be any issue in those weeks. That's why we have merged those 2 weeks. Okay. So 2 to 4 and 8 to 10 are both fine. Yeah. So 2 to 4 we are putting that. Like I'll ask them to update in the calendar. Okay. So how many of you have seen the lectures of 6 weeks?
So week 5 or 6?
With 5 to you must have seen, I guess, because 6th is too late, right? 6th also it's a bit late only, but you have to submit it by 12. So we'll discuss everything tomorrow. The 6th week doesn't have much content. Like only the SBD part is pretty difficult to understand. And then the positive definiteness is pretty simple. So most of the questions are from positive definiteness in the graded also. So I don't think we will face any issue in solving the graded assignment. Only the SBD part is a bit tricky or difficult, you can say. So 6th week, nobody has seen the lectures, I guess. Huh? Okay.
No, sir. Haven't completed.
Oh, so 5th week we have seen, right? 5th week has been discussed by Ram also, everything, I guess.
Yes, yes.
Yes, sir.
There was a session day before us.
Okay, so 5th week is done. I'll just go through
Yes.
the activity. Those questions are pretty simple. One more thing. Do you know how to solve the eigenvector and eigenvalues? How to calculate the eigenvalues and eigenvector of complex matrices? Like anybody has any issue in those?
So it is the same, right?
Same. Okay, I'll just give you one question. Just try to solve that. I'll just write it on the pad itself and yeah, I'll just try to solve so that it becomes simple. Like in 5th week, only you have to only eigenvector generally gives a pain. Otherwise, the proofs and all is fine, but the proofs and all generally nobody generally asks. Okay, you should be aware of the result, how generally is the result, like the diagonalization, how generally it works and all. So why generally we do the diagonalization? So if the matrix symmetric, real symmetric, what will happen? If the matrix Hermitian, what will happen? Okay, these are all the spectral theorem, but I'll just give you one simple matrices of 2 cross 2. That is pretty simple. Just try to solve and give me the eigenvector, not the eigenvalue. It's pretty simple, but give me eigenvector. And I'll ask you the method also. How did you proceeded and how did you get that? Okay. So I'll just share my screen now. Is the screen visible now?
Yes, sir, it's visible.
So if I have a matrix, so tell me the eigenvalues first. And then the eigenvectors.
So eigenvalue is the plus I and minus I. And the corresponding eigenvector is
Plus and minus I.
Minus
This is
1,
a-
plus and minus 1.
Can't be minus
plus,
I.
plus,
It's a
sorry, yeah,
Herm-
plus and minus 1.
It's a Hermitian matrix, right?
Yeah.
How
Yes.
come the value eigenvalue would be a non-real?
Plus minus 1, yeah.
Okay. Okay. How will you calculate the eigenvector? So first eigenvector for lambda I. So tell me the eigenvector. Okay. The eigenvalue was pretty simple. And whoever
The
many
first
other
vector
person-
is 1 minus I.
1 minus I. Okay. Given the unit vector. Okay. So this should be root 2. Fine.
Yeah, sorry. Unit vector 1 by root 2.
As a U2.
And U2 will be, this is 1 and I. 1 and I.
Both 1 and I, you are saying. Okay, this is the one option.
No, both 1 and I, no? The second one is I means I square minus I 1.
Okay, so B option, what you told? 1 upon root 2, 1 minus I. 1 minus I.
Minus I 1.
Okay, minus.
1 minus, yeah.
Okay, 1 minus I.
Or 1.
Any other answer from anyone? Anyone who has solved this? This is pretty simple. I'll give you one difficult one also. So this is the first simple one. Anyone else? Okay. So out of A and B, which is correct? Just type in the chat box itself. I'll just see.
So your voice is not clear, sir. I'm not.
Okay. Yeah. So out of this A and B, which is correct? Is this fine now?
Yes, now a little better.
Okay. So B, somebody has told B. Now the voice is fine, I guess, right? Without earphone, I guess it's fine.
Yes, sir. It is. So it is the second one, right?
Yeah. So second one is correct. Okay. First one was pretty like the
the whatever the options we have given is too bad. Okay, so anybody can guess it. Okay. So yeah, can somebody unmute yourself and can tell me the procedure?
Actually, so it's a simple one. So just getting the value lambda and then setting for the ax equal to 0.
Okay.
That's all.
So one was the lambda is equal to 1, right?
Mm.
So a was 0. Okay. So 0 minus 1 I. What was that? I
I 1.
minus 1, right?
Mm. Mm.
And then xy equals to 0. Okay. So you got two equations, right? And from here, how did you solve that? So main. Okay. So this is the one equation and this is the second one. Okay. How did you solve? The most important thing is to solve this equation. Okay. So this and all, everybody can write this. Okay. How did you solve this one?
But sir, actually, I
Like,
didn't form this equation because it's so simple. Ki I just making how I can make it 0 and directly put that
Okay.
1. And,
Okay. So you took x some value so that the equation will get cancelled. Okay. Right. If you'll get, okay, this was a pretty simple one. If you'll get some, okay. How can we change this? So the one thing is, whenever you'll get this type of equation, so you are getting two equations, right? This is not x, this is x1 and x2, right? So in the x itself, this is x1 minus x1 plus I x2, right? So what you can do, see, whenever you are having 2 cross 2 now, okay. So whenever you will be having 2 cross 2, so this must be the multiple of this one, right? Are you getting my point? Because whenever you'll change that this matrices into that row linear method, what is that? I'm not able to pronounce it clearly, but you have to make this 0, right? In those methods. So when you'll make this 0 in the 2 cross 2, most of the time you'll see this will be the multiple of this form. So you don't have to worry about the second line. You can just write one equation, okay, and get the value. Like now you're having only one equation and you have two variables. So you have to assume one, right? So you'll assume this as a k and then you'll get this one, right? Are you getting the point? So whoever doesn't get, many of the person doesn't get the idea how to solve the eigenvector. Okay. So what you can do is whenever you are having 2 cross 2, so just write one equation itself. Okay. Because you are having only one equation with two variables, take the one as a k or something like 1 or I, whatever you want to take, and you will get the second part also. Okay. And this is a span of the first eigenvector. Okay. Because with this span, we can get many number of eigenvector, right? This is the first. This is the u1 you'll get. Similarly, you can get the u2 also. Okay. So you'll just write a plus lambda, and then for 2 cross 2, you don't have to do anything. You just have to solve one equation. You'll get the value. So for 3 cross 3, how will you do that?
Excuse me, sir.
Yeah.
Over here, you normalize that, right?
Yeah, this is the normalized form.
So we have, like, do we have to, like, is there a problem if you don't express it that way?
What can you, like your voice? I'm not able to get your voice clearly.
Like, do we always have to normalize it? No, right?
Yeah. Without normalization, also your answer is correct. Because it will be in the, if you have been asked to get the unit eigenvector, right? So then you have to normalize it. Otherwise, if you're not normalizing it, you can take k also, right? And ik.
Yeah.
And then if you'll normalize, the k will get cancelled. So the thing is, if you have been not asked, you can write whatever. But if you have been asked regarding the unit vector or the normalized form, that will read in the SVD that every time you have to take the normalized. Okay. So this was, yeah.
Like you do for the unit, for the eigenvalue.
Yeah, correct. So one more equation is there, I guess. One, two, put it three.
It's 1 plus
Tell me lambda 1 and lambda 2 here.
sir, it's 1 plus a, right? Delete
1 plus iota. Sorry, this is 1. This is 1 plus iota. This is 1 minus iota. This is the diagonal elements are 2 and 3. And one more thing, that in the exam there was some error, right? Somebody was saying
Yes,
in the discourse.
yes, that a to the power 4.
Okay, so a to the power 4 was, so the given answer is 1297, right?
Yes, sir.
So how many of you have given the answer 1297?
I given.
Okay, so you gave, and most of you have given the answer as 2. Okay.
Sir, how to get that 1297?
So 1297 is generally the summation of the diagonal element.
Nay, what is the interpretation of the instructors that the question is meaning?
What?
That one property is there, na? A is equal to ace of lambda s inverse. So when you are keep on increasing the power, a to the power k is equal to s into lambda to the power k of s inverse. So
Yeah.
in the given matrix that lambda is given, so to the power that diagonal factor you will get, and just same will come for the a4 and the plus of that. That's all.
But so in the question, it has, like, they asked for the total sum of a to the power 4, right?
Yeah, the question, it was the printing mistake, or you can say whatever the mistake. So the assumption was to ask the diagonal element, but mistakenly it was written as. But
No,
you'll
sir.
get the, so you'll get the marks for sure. So you'll get mark for 2 also, and that 1297 also. Okay, so don't worry about that. So I thought of writing on the discourse, but it's fine. I just told you here itself. So while signing off the marks, I'll make sure that both of the answer will be correct. Okay. So yeah. So, and most of the questions were pretty simple, right? So straightforward, like pretty simple. But the next quiz will face a bit difficulty. So make sure you prepare well for this second quiz. Okay.
So
Yeah.
what about the marks for this? There is one reflection thing or something, right? From the discourse, it was announced recently. Like, will that
Okay,
marks also be added for the final?
That's regarding the bonus marks. You get some bonus marks out of 5. So it's better to solve that. It's pretty simple one. You can just solve, and then you can submit it before whatever the deadline is there. So you'll get some 5 marks extra. So it generally helps. Like last time, what happened? Last time that was not regarding to reflection questions and all. Last time it was like discourse or live sessions and all. So many of the person got benefited from that. I can see that the many of the person who were at the border generally got the good marks. Like that generally helps them to pass also. And many of the person who were at like 85, 86. Last time it was like 10 marks, I guess. And many of the person who were at 80 got 90 and got the script. So it generally helps a lot, the final marks, right? So it's better to solve it, not take much time. How much time it will take? Maximum.
Which assignment, sir?
That reflection assignment. I'll show you.
Hey, it is
Everybody
not,
is aware
it
of
is
that,
not
right?
10%. Yes, sir.
Yeah, so it's here, and
Okay,
then you have to solve. So then submit it, whatever the deadline is there. Before that, you can submit it. Okay.
okay, sir.
So solve this one.
Yes, sir. 1 and 4 is the eigenvalue, and
Okay.
the corresponding eigenvector is 1 minus I minus 1 and 1 plus I.
Okay. So lambda minus 4i. Okay. So 2 minus 4 is minus 2. 1 minus iota, 1 plus iota, minus 1. Okay. How did you solve from here? Now you are having two equations, right?
But actually, I'm solving without putting the x and y, just taking the mentally what is the value I should put this row column so that it get cancelled. And
Okay. So what is the value you are taking for here, x1 and x2?
sorry?
What are the values you are taking here, x1 and x2?
X1, x2, I take 1 and 1 plus I. X1 is 1 and x2 is 1 plus I.
Yeah, this is correct. Anyone have any difficulty in solving this type of questions?
No, sir. Like otherwise as well, like we can just if it gets to the
See.
3 by 3 scale as well, we can
Huh.
use it using, we can solve it using linear equations, right?
Yeah. And one more thing, 2 cross 2 is pretty simple because this must be a multiple of this one, right?
Yes.
So with the one equation you can solve. So no need to solve the both equation and then get x1 and x2. So this is already the multiple of this one. So you just have to write one equation and then you'll get the solution, like minus 2 x1 and plus what 1 minus 1 x2, and then take some, assume one value because you have one equation and two variables, so you have to assume one. Okay, so you have assume, so whatever you want to assume, you can, whatever the value x2, you can take 100 also and then calculate x1, so it's all right. But with the but if the options, 4 options are there, then you have to choose correct, like wisely which option, like what values you have to choose so that will match up with the options. Okay. So this was done. So I'll go through the let's say the activity questions and practice. Those are also pretty simple one. I'll just go through the graded also. If you are facing any issue in the graded also, you can just ask. I'll not solve the question. I'll just tell you how to do that, so that you'll be able to submit it. Okay, today itself, so that we can start the 6th week tomorrow and then complete it by Friday or Saturday. Okay. The 6th week also. It's too hot here. So the first one is like a statement that the inner product of two complex vectors is always commutative. Why this is false? Can somebody reply that? But first tell me whether it's a, like, I already shown you the answer, but it's a false statement. But why it is false?
Because x bar dot y will not be the same as y bar dot x, like, because of that star.
What? X bar?
X bar dot y, like x bar times y,
X bar times y.
like it won't be the same as y bar times.
Yeah, that's correct one. So x, generally x dot y is what? It's not equal to y dot x, right? This is what commutative things mean. Anybody else is having any issue in this? Like, it's a pretty simple one, but we have to go through every question. So I'm just as a formality, I'm going through that. If you're having any issue, you can just stop and ask. So yeah, maybe mostly the conceptual part generally comes in SVD. So you'll face issue in SVD. So B come tomorrow for the session. So SVD will be facing issue. So discuss.
So you can directly go to the, it's from the practice assignment.
Okay, so the practice assignment also doesn't. Okay, I'll just go through that. Practice assignment, where is that? I'll just go through that also. If somebody is having issue, you can ask. Otherwise, okay, it's fine. So, okay.
And there is a finding eigenvalue, eigenvector, 3 cross 3 matrix is there. there maybe you need
So this is the
some.
first one, the complex conjugate. Everybody knows that how to calculate the complex
Yes.
conjugate.
Yes.
Okay.
Yes.
The second part is complex. Okay, transpose you have to calculate. So you have to do the conjugate also and then calculate the transpose.
Transpose.
Okay, the inner product is x bar or into y, right? This you can calculate. Then the square of the length of the matrix. Okay, this is a simple like inner product of x with itself.
Yes.
Okay.
Yes. Just multiply with the conjugate transpose.
Or you can calculate by this method also, like square the
Take the
each
square
every-
and add. Yeah.
yeah.
But sir, can we do when the means the vector is in complex domain? Then to calculate the inner product, we always have to use x conjugate transport dot x.
Yeah.
This is what we are doing. X transpose dot x, like not dot x. We are multiplying with x.
Yeah, we always have to go in this method, right?
Yeah, if the complex number is there, so, or you can calculate with this method also. x1 ka bar ka whole square, x2 ka bar ka whole square. This is also one method to calculate the length, because you have to calculate the length of one vector only. So either
Since
you
it
can
is
calculate
one-
with this method or with this method. Both are same. You'll get the same.
Single dimension.
Yeah.
Single dimension.
Yeah, single dimension.
Right.
Then
Sir, for
Yeah.
this, no, not this one, next one.
okay.
So to this type of problem, we always have to check this, means A transpose A is equal to whether it is identity matrix or not. Then only I can call the unitary. Is there any other method to shortcut so that we can?
So what is the property of unitary? Like all the columns should be orthonormal, right? So orthonormal means the
Dot product
if
equal
you-
to
not dot, like the length should be one, right?
Yes.
For each column, the length should be one. This is the one method. Okay, and one other
Method.
property of the unitary is what?
A transpose A is equal to
Equals
identity.
to 1.
Okay,
Yeah.
that is fine. That is fine.
For the row also we can do the same, right?
What row?
For the if it is unitary, the row will also be orthonormal, right?
Not the row, the column one. The row would be pretty. The row, the column, the length of each column should be one, because that is orthonormal. So the property of orthonormal is that the summation of the length, or you can say the x1 whole square plus x2 whole square, everything should be, the summation should be one, right? That is orthonormal. And one more property is there of the unitary. What is
It
that?
has to be orthogonal also.
Okay. So for the orthogonal, what to do? You can take the dot product and then should be zero, right? Okay, so that thing is pretty simple now. You have to, okay, if that is a 2 cross 2, then you can just see whether all the columns have the length 1 and the dot product of each of the column is 0 or not. That is the one method. Or you can calculate the transpose also. That's the, like, if you want to, that's your wish. Right. So here you can directly see that the length, I don't know, you can calculate the length also, it seems to be 1, but the dot product is pakka will not come to be 0, right? Because everything is on the positive, right?
By root 6 by root 3, yes.
Yeah. What is that? Like it can be in some cases, but not always. Somebody is saying something. But here, so have you got the point?
Yes, sir. Yes, sir.
So you can do that method also, or whatever the basic approach you are going through, A transpose. But see, if you are having 3 cross 3 matrices,
Then it is very big.
yeah, then it becomes very big. But see, if that is a 3 cross 3, the length of each column can be seen, right? Whether it's coming to be 1 or not, right? But to calculate the orthogonal, you have to get 3C2, like, yeah, so
Yes.
2 pairs you have to take. So 3 pairs there, A,
3
B,
pairs
B.
I have to check.
Yeah, 3 pairs you have to check. But if you're calculating A transpose A, there also you have to do a lot of multiplication, right? So this is a 9 and 9. So every time you have to see 9 multiplication, not 9 multiplication, more than that. 9C2 from here, 92 9C2 from here, and then you have to do the summation also. So that again is going to take a lot of time, right? So it's better to go with this approach.
So, but
Particularly, sir, in the question, if you go down, where we go down, sir, down,
Well, okay.
down, down, go down. Next one. Next one.
Oh, how many questions are there? Okay, this one.
Next, not next one. Yes, this type of question I have to check how many times. I'm just asking.
Yeah.
sir, excuse me, sir.
Yeah.
Sir, for unitary, I think this orthonormality is there for this clause as well. Because if you when you take a unitary matrix and you have this A star, U star U, that will basically be identity, right?
Yeah.
So the transpose of that unitary will also be basically the conjugate transpose will also be a unitary matrix, right? For
Yeah.
unitaries. So in that case, then that would be similar to saying that the row of the unitary is also orthonormal, right? Because if A's U star is unitary, then the column should be orthonormal. So that would be the same as the row in the original U being orthonormal.
I don't think so. It will always be there. For the row. We can get some example. Okay, I'll try to get some example. Yeah, say.
Yeah, I have just problem in practice assignment question number 8 and 13. If you can, after this, you can just solve.
Okay. So his doubt is, it's not doubt, like he's saying, if all the columns are orthonormal, this is what you are saying, right? All the columns are orthonormal. So if x1 squared plus x2 ka squared is equals to 1, and y1 ka squared plus y2 ka squared equals to 1.
So it's not normal, sir. It is orthogonal. Rows are orthogonal.
No. Rows are not orthogonal.
This is not possible, right? Like it can be possible for some.
Sir. Like, sorry. So the reason I said is because let's say, okay, this is a unitary matrix U, right?
Yeah.
X1 square. It's okay.
So this
that
is the
means
x1 and then this is x2. Okay, this is y1 and this is y2.
Yeah.
Okay.
So U star would be like conjugate of
Transpose.
conjugate transpose, right? So that would be like x1 square bar, and like you basically take the transpose and take the bar of everything, right?
Okay, this is one example of Hermitian, right? And then I'll divide it by the length. So it's the length of 6. Okay, this is Hermitian, right? Okay, so but so for this case it is fine. For this case, row also the summation is 1.
Yes, like, even without that, so if it is unitary, U star into U will be equal to identity, right?
Yeah, this is fine.
Okay, that means if we take U star to be a unitary matrix, then U would be U star star, right? That means that is how we get U, basically. Like using the property, we can, like U star, the whole star will be U. So that means U star will also be a unitary matrix, right?
I don't know whether I'm not able to get what you're saying.
There is
Or
an online one website is showing that it is that way. It is what he's saying.
Yes, like the reason I said is
That is the properties of unitary matrix.
if you take like U is the original unitary matrix. So
Okay.
U star U is identity. That is the basic property of unitary matrix. Now,
Okay, you used. Oh, okay. Yeah, I got your point. So you are saying if U is a unitary method, unitary matrix, so U star will also be right. So what we are doing here,
yes,
we are just transposing the column into rows, right?
yes.
Rows into column. So if one, yeah, I guess you are like saying correctly, because U is a unitary and the summation of all the columns here is one. So if you are changing this to U star, that is also unitary. Okay. So here also the summation of the rows or the column will be equals to one. Okay. Yeah, I got your point. Yeah, thank you.
So
Okay.
It is saying
I
rows
was
are
saying
also
that
orthonormal, sir, in addition to column.
Okay. So rows are also orthonormal, right?
yes, so that might be a bit easier, like I think in some cases.
Okay. So both are orthonormal. So that I need to, but whatever is saying, it's perfectly correct. But I'll check it once again, but it's fine. Okay, so that method is also fine. So we can, yeah. So here also you can see the summation is one here, also, yeah. But you have to go through the, if one part is that, like the orthonormality is there, orthogonality also you have to check, right? So you have to go through the dot product and then you need to check whether the dot product is zero or not. That's the one method. Or you can do the transpose or the conjugate. You can just multiply it with the conjugate transpose, and then if you are getting unitary, it's a unitary. Anything better than this? Like anybody is having any concept like better than this? How to check the unitary?
We can use the other one, like if we multiply that to another method, that is more intensive.
Yeah.
The length remaining the same. I think that will be more intensive.
Okay. So check the length and then check the. Okay, this is the
Like
length.
AX, like the absolute value of AX would be equal to absolute value of X. That right?
Okay. Yeah. So somebody has sent me this link. Okay. So it's clearly written in the matter. Yeah. It's fine. So this is the matrix, I guess it's given here, right? This is the matrix, this matrix. 1 upon root 2, 1 upon root 2, iota. So I guess, right? Yeah, so which question now we have to discuss? 8th.
Question 8 and 13, sir.
Okay. So 8th is, what's the
Actually,
issue?
I'm not getting the answer. That is why I'm asking. If you can solve this.
Okay, I'll solve this one. So do you have the solution PDF?
Sorry?
Solution PDF do you have?
No, I'm just solving in my pen and paper.
Okay. We'll just open that solution PDF. Okay, it's not uploaded, right? I'll just upload this, right? I'll just upload on the portal also. Okay, I'm not able to upload this file. Okay, so 8th one. Okay, what is this, man? Okay, I'll solve this. Okay, tell me the matrices. Tell me that element
Yeah.
of the matrix.
1 minute.
3, 2 minus
3.
1. Arrows, it is 3, 2 minus 1.
Minus I.
2 minus iota.
2 minus I and minus 3i. 2 plus I, 0. 1 minus I.
1 minus iota. Okay.
3i,
Hmm.
1 plus I and 0.
This is what we have to do. Plus 2 minus iota. So this con. Hey, what is this? Okay. So minus lambda into 2 plus iota minus 1 minus iota into 3 iota, right?
Oh,
So
so this is plus 2 minus I or minus?
where?
Yeah, it should be minus.
No, sir.
Outside, sir.
Outside, sir.
Before the square bracket.
2 minus iota, right?
No, before that, it will be plus
There
or
should be a
minus.
minus. It should
Minus.
be minus 2 minus I.
Okay, this is minus. Yeah, correct. Plus, so minus 3 iota. 1 plus iota. 2 plus iota. Minus lambda 3i, right? This is fine.
Yes.
Hmm.
Okay. So this I'll solve it. This is what? 2 plus iota plus 2 iota minus 1 minus plus lambda plus 3 iota lambda, right? And this we have to multiply 3 iota. So we are with what? 2 plus 3 iota minus 1. So 1 is this 1 plus 3 iota. We have to multiply with 3 minus 3 iota.
Minus 3 iota
3 iota plus 9
Plus 9 lambda.
minus
Plus 9.
9 iota square lambda. So this is plus 9. Okay, fine. I'm here with 9 lambda, 9 minus 3 iota. That I can subtract, this I can reduce. So this was correct, right? So we didn't made any mistake here. Now we'll do this one. This we have already done. Okay. Now we are left with this one. So minus 2 minus iota. Minus 2 lambda
minus
plus lambda. So 3 iota plus 3. Fine. Now
So that is minus lambda iota.
minus lambda is it? Yeah.
oh, minus lambda. Okay. Now we don't have anything that can come common. Nothing. So now this 2 minus 4 lambda minus 2 lambda iota minus 6 iota minus 6, right? And then minus plus 2 lambda iota minus lambda plus minus 3 plus 3 iota. This is fine, right?
Yes.
Okay, so what this can be cancelled. Anything else will get cancelled, nothing. So minus 5 plus 5 by lambda. This got cancelled. 6 minus 6 iota plus 3 iota. Okay, this was got cancelled. So minus 9 plus 9. So we are left with 9 lambda plus 9 minus 3 iota. So this also got cancelled. So we are left with 14 lambda plus 18. Okay. So this also got cancelled. Okay. So yeah. So all the iota part got cancelled. Now we are left with only lambda. So this is what? Minus 3 lambda square minus 6 plus lambda cube plus 2 lambda, right? And from here it is 14 lambda plus 14 lambda plus 18. Okay. Okay. So this minus 3. Okay. So lambda cube minus 3 lambda square plus 16 lambda plus 12. Okay, solve this one. So can you see can you tell me the one root of this? One root would be agar if you put 1 here, 1 minus, no, it's not going to be, so minus 2, okay, minus 2 minus 32 plus 12, minus 2 is minus 8. Okay, this also will not cancel. So 2 plus minus 3, no, this will not get cancelled. Can you tell me one root of this?
Is in minus sign, come with minus sign, and 3 lambda square come with plus sign.
3 lambda square will come with plus sign.
Lambda cube with minus sign, because I had solved it
Sir, it
yesterday.
should be lambda square minus 2, not minus lambda square minus 2. The 3 minus lambda.
This one, like lambda cube minus?
No, sir.
No, 3 minus lambda into.
Yeah.
Here it should be.
Okay, 3 minus lambda into?
Plus lambda square.
Plus lambda. Okay, yeah. This minus lambda. Okay. I forgot what was that we got earlier. 14 lambda plus 18. Okay. How will you solve this in exam? Okay, so this is 3 lambda square minus 6 minus lambda cube minus 2 lambda, right? Plus 14 lambda. That was 14 lambda, right? I forgot what was that. Okay, I should put it from here also. So we have minus lambda cube plus 3 lambda square plus 12 lambda plus 12 equals to 0. So I guess now we have, which is the lambda is equal to 1. No, lambda equals to 1. It's not the root. Tell me one root. Minus 2. This will become.
Sir, you can directly find the root.
3 minus 2 and plus 2 are the roots.
It will be root 2 minus.
Okay.
3 and a root plus or minus root 2.
3 and plus minus?
Root 2.
Root 2. Okay. This is the equation everybody is getting, or I did some mistake because see iota got cancelled. So for I guess we are correct. Okay, I'll just, oh, this is not the equation here. We are doing some mistake, I guess. 16 lambda. So this was 14 lambda that we got earlier. Okay.
Yes,
So maybe some error is there.
It's a plus
Okay,
2
sir.
lambda, lambda cube minus lambda cube plus 2 lambda is there. Multiplication. Yeah.
Okay, minus plus. So plus 16. So we are left with what? We are left with lambda q minus 3 lambda square minus 16 lambda minus 12 equals to 0.
Plus 16 lambda, sir.
Like I multiplied with minus everywhere. Okay.
Okay.
So now you can get the root. Like you can get the calculator you'd be having, right? You can get the root. One calculator generally calculates the root of any equations. Do you know that? The minus 1 is the root 1. One root, just I want one root. Okay. So lambda plus 1, you can divide this, right? To get the other root. Minus 1 is the root, pakka. Minus 1, minus 3, plus 16, minus 12. So yeah, this is the root. Minus 1 is the root. So now you can get the other root also. So lambda square, if you multiply lambda cube minus lambda square. So you'll get with this plus, this got cancelled, minus 2 lambda square minus 16 lambda minus 12. So this you can write what? Minus 2 lambda square minus 2 lambda. So this got cancelled now. So minus 14 lambda minus 12. Oh, some mistake. Now also we are doing lambda. Okay, this is plus, right? This plus. So this is plus, and then we'll get 6 minus. Okay, so minus 4 lambda square minus 16 lambda. Right? Then we'll get some, what is that? 4 lambda minus 4 lambda square and then you'll get how much? Minus 4 lambda. So now if you calculate the plus, I'll be having 12 lambda minus 12. Now you'll get some minus 12. So minus 12 lambda minus 12. So this you can do plus 1 and then what is that? Lambda square minus 4 lambda minus 12. This you can solve with the linear equation. So the quadratic equation, right? So you'll get the. So is it correct?
Yeah.
6 and
6 and
minus 2.
minus 2. So minus 1 minus 6 and minus 2.
Actually, in my equation, I am not able to eliminate that I. Maybe some mistake.
Some mistake. I did so many mistakes. You also are doing some here. So it's fine, but in the exam you should not do. But in exam that this type of question will not come for sure. I'll make sure this type of question. Yeah. I'll just go through the quiz. So we have already prepared, but I'll just go through that. We don't have this type of calculation in the exam.
So then question 13, sir.
Okay. Okay, I'll just go through this one. Okay, what is that? 13? Let U and V with the symmetric matrices. Then consider the following statement. So U and V. So you can just take some 2 cross 2 matrices that is symmetric and just try. So U plus V will be symmetric. That is for sure, right? I don't think so. This.
Yes, that is there.
Okay, so U plus V will be symmetric and U multiplied with V. So if you are having some symmetric matrices, so if you'll do some, just think about that. If you'll do some like calculation, so there can be some portion after multiplication will not get the symmetric value, right? You can just try this equation, this statement. You can try with some 2 cross 2 symmetric matrices and just try to calculate the U and V. Multiply that UV. I guess you'll be able to get that. But this is not correct for the Hermitian. For the Hermitian, I guess you multiply the product generally comes to be Hermitian, but the summation generally doesn't come.
Yes, sir. I get confused over here when they said ki there is two symmetric matrices. My confusion is these two matrices, whether I should consider from the real space or the complex space, or I should consider
real.
from the where it is written.
Okay, it's not written. It's not written that this matrices are square or not. That is also not written. Right.
So symmetric means like it can be real as well, right?
Symmetric. Generally, whenever we talk about the symmetric, generally we talk about the real symmetric, right?
Yeah, because Hermitian is not really symmetric. Right?
So you have to take the real symmetric only.
Symmetric means I always have to take the real symmetric, but there is means no matrix is there which is in complex plane. Can be there, na?
Symmetric, how come it can be symmetric? Yeah. It can be symmetric and complex also, because see, for example, you are taking 2 cross 2 with diagonal matrices 2 and 2, right? Or 1 1, whatever you want to take, KK, and then you can take the second value, the first row, second column, you can take some iota.
Yes.
And the same iota you can take. So this is a symmetric matrices, right? Okay, and then try to calculate this. So I'll just take
my confusion is only there. Initially, I get confused this space from where I should consider. Shall I consider from both or only real?
Okay, so see, if somebody is writing, it should be real, but if it's not written, I guess so he just want to confuse you. I guess he's asking about both the equations. So this question, I don't know who said this question, but I guess he's asking about both symmetry, real and complex solves both. So this is U, for example, this is V. You can take some example, like tell me one, and this can be 2 iota, right? So if you do the summation you don't have any issue, right? You'll get the 3 and this 3i. So this comes to be symmetric, whether it's a real or complex number. Okay. Only the problem will come when you are calculating UV. So if you are doing UV, so UV, if you are calculating, pakka you'll get some different value, right? Whether it's a real symmetric or, like for example, this is 1 1 and 2 iota. Say for example, iota is not there. This is 1 1 1 1. And this is 2 2 only. Then also I guess you will not get the symmetric matrix, right?
Yes, sir. Right. It is.
Sir, in some cases, you will get symmetric matrix. That is only when UV is equal to VU.
Yeah, UV is equal to V. Okay. UV is equal to VU means what? Okay, you'll get a symmetric matrices.
Yes.
So
in
generally that happens in the
UV is equal to
And see, if you are considering this UV equals to VU, then it will always happen, because see, even if you are having U as a rectangular matrices also, and V as a rectangular matrices, like for example, 2 cross.
Can't be rectangular, sir.
See, I'm telling you, 2 cross 3. Okay, this is a 2 cross 3. I'm just telling you the example. It's a 2 cross 3 and this is a 3 cross 2. So you'll get 2 cross 2 matrices. Okay, but it can't be symmetric. Okay, fine.
The definition of symmetric matrix is a matrix.
Yeah. No.
Square.
I'm just telling you an example. Yeah. So rectangular can't be symmetric. That is pakka. So yeah. So this will not happen for the rectangular. But in SVD generally we do the different thing. Okay. So I'll read it maybe tomorrow. Okay. So he told if we are able to see this UV equals to VU, then it will hold. But for other cases, it will not hold, right? See, for example, I told you one example. So whether you are taking iota or not iota, that UV will not give you some symmetric matrices. Okay, even both are symmetric. So it will not happen for the complex also, or for the real also. It will not. So you just have to take some examples. So see, there are so many, like, what are you going to say, the property of the matrices that you can't remember. So you have to do some hit and trial method. Just take some basic example and then try to solve it. So you'll get that. Okay. It's not that whatever you're taking till, so see, you can have some assumption in the mind. Okay, this happened for this. Maybe this would have happened for this matrices only. But not, it will happen for most of the matrices. Whenever you'll take some simple matrices, no, you'll not get the symmetric matrices.
No, sir. Yeah, that part is okay. But when our approach is through hit and trial, maybe on that instant.
Yeah. This is what I'm telling you.
Yeah.
Maybe for some instant, whenever you're taking the hit and trial method, you took some very basic matrices that happened for that matrices. Okay. So for example, you took some U and some V. And for that UV, you took some basic example like 0, 0, 1, 0, some basic example. And then you calculated that UV and you were getting this as a symmetric matrices. Okay, but see, this can happen anywhere. So if you are choosing for some UV, for some symmetric, like for example, 0, 0, 0, 0. This is symmetric, right? And V also will take some 1, 1, 1. So whatever you will take V, that doesn't matter. Every time you will get UV equals to symmetric one, right? So you don't have to choose this. Whenever you are choosing some hit and trial, don't take the exception thing. Okay, so just take some basic matrices if you are doing any question with the hit and trial. Okay. This somebody told regarding this. If you are able to get UV as VU, so every time that UV that matrices will be symmetric whenever you will multiply with this V matrices. Okay.
Okay.
So
yeah.
So what is that? That if UV equals V, it will be symmetric.
What UV?
Like what is the last part you said?
So if U into V, if you are getting some matrices, U multiplied V equals to V into U.
Yeah.
Then this UV will be symmetric. This is what you told, right? Somebody told. I have not, like, okay, I'll just go through. Can you have any matrices? Okay. So we can have, okay. So you can take 0, 0, 1, 1. And this V, we can take some matrices. Symmetric, okay. 1, 1, 0, 0. This is also symmetric. Okay, the multiplication part, VU. So if you multiply this, you'll get 0 everywhere, right?
Yeah.
So if you, yeah. So here VU equals to, UV equals to VU. That is happening. So UV is a symmetric matrices. This is what you were trying to say. So, like, who told this method? Like somebody told, I guess. I don't remember his name.
Sir, yes, sir. It is a property where I read that is one of the properties of symmetric matrix.
Okay. So this will hold everywhere. So this, whenever you're having some matrices UV, and if the product of UV and VU is same, then the UV will be a symmetric matrices. Okay. So this will hold for every time below. So there are so many other properties also. You can just read from Eigen. So yeah, any other questions from practice, or should I go through the practice?
Yeah, Sevens. We are going in order, right? Before.
Okay, I'll just go through that. So activity is not required, right? So activities are very basic. So
So first we'll finish practice.
Okay, I'll just
We
go to the practice.
completed hard problems.
So the first one don't have any issue. Second one also you have to calculate the complex conjugate. The third is the inner product that you already know. The square of the length is, if you have to calculate the square of the length, you have to do the inner product with itself. So this is a, if you have to see the unitary that we have already discussed, you can go through the that you can calculate the, what do you can say, orthogonal, like you can check the orthonormality of the each of the rows or whatever, or the column, and then you can check the orthogonality of the column. That also you can do. Hermitian, tell me this is Hermitian or not?
It is, sir, because
Yes.
no
Yes.
imaginary
Yes.
things are there, and it is also symmetric.
No
Transversal.
imaginary thing is not the correct.
Means because it is normally A equals to A conjugate transport, right, sir? Because
Yeah.
nothing is there.
So which of the following matrices the Hermitian? This is also, I don't think we'll be having any issue in this. Okay. Tell me that fourth one is, this one is symmetric or not symmetric, Hermitian or not?
Yes, sir.
Yes, Hermitian.
Okay. The eigenvalue we have already calculated. This also you can see. So how generally you calculate the unitary is that, like a, you can do that thing like A transpose, like A conjugate transpose into A, you can multiply and then you have to get 1. So from there you can get the value of K. That also you can do, or you can do some OR method. How will you, okay.
So you told column adding, right?
Yeah,
sir?
yeah,
1
column
plus A.
also, yeah, the area, that the area I'm saying, the length of this column should be equals to 1. From there you can get, right? So this is K multiplied with 1 plus iota and K multiplied with 1 minus iota. So from there also you can get the value of K. Similarly, you can get the value of K here. So you can just do the ortho, you have to fulfill the property of the orthonormality of this column, and with this you can get the value of K. And this
Sir,
is
when I am taking this Q transpose Q is equal to unitary matrix and equating the value, and I am getting K square is equal to 1. So
K equals to 1 you are getting.
K square is equal to 1.
Okay.
So on that time, ideally K's values is plus minus 1.
But this is in the root, right? So minus 1 can't be. See, from the starting you have to take the, okay, so see this, in this problem, according to the option, K equals to 1. One thing. Okay. The other thing is they have not written K is real or, so he has not, like whoever set the question has not defined the K. So according to the option, the K should be one thing. Okay. And the other thing is, whenever, if you have been given K is a real value, right? So whenever the K is a real value, so whenever you solve some equations and that is under root, so you have to take the value which is real, like not the minus 1, because if you take the minus 1, it will become a complex number. Like whenever we solve in the childhood, when we used to solve some problem that, and that in that thing, if something is under like root x, whenever we used to solve, we used to take the x as some real value. Are you getting
I got your point, but actually the problem is since the under root minus component, when we are only thinking about the real space, I can jolly well eliminate that and can think. But since we are now dealing with real as well as complex place.
Yeah, this is what I told. Because it's not written here, it's not been mentioned regarding the K. So you have to go to the options. If the options was minus 1 also, then you have to take both, I guess, 1 and minus 1. But in the option only 1 is given, right? And
that means, okay, since it is not in option, it's easy for me. But when both in option, I believe they are both should, I can able to select that option also is there. But ideally minus 1 can happen.
Yeah, it can happen.
Okay.
Because
that is my only
question.
question.
We are talking about the complex, everything is complex. This one can also happen.
Okay.
Okay, so the next one is A has been given, and then A, if A can be factorized. So this is simple diagonalization. Okay, A has been diagonalized in this U, D, U, and then with U denoting, so it's a unitarily diagonalizable. D is, okay, so D, you can calculate the eigenvector and this, sorry, eigenvalue and eigenvector and eigenvalue, both you have to calculate. So if you'll calculate the eigenvalue, so it will come in the diagonal part of D. And if you calculate the eigenvector and also take the normalized form of eigenvector, so you'll get this. So this is U1 and this is U2 that you have to do. That we have already seen how generally we calculate the eigenvector of the 2 cross 2 matrices. Okay. And now you are having which of the following is a unitary, so that you can say hit and trial or whatever you want to say. So like if you want to calculate with a basic approach, you can calculate. Otherwise, you can just go through that, see the rows or column whether it's a orthonormal or not, and also take the product of take the dot product of the column. And if you are getting 0, like you just have to see whether it's a orthonormal all the columns, or like if you are taking only columns, so take the column only. If you are taking rows, take the rows, and see whether it's orthogonal or not. This also we have discussed. So I'll just go through the graded also. If you are having any issue, just tell me. Otherwise, simple one.
So can I ask a doubt regarding the upper triangularization?
Upper triangular, the proof you're asking?
The proof is basically the method, right? It is basically the method of solving, right?
Yeah. So what is that in the upper triangular matrices?
So my doubt is if it is Hermitian, it is well and good. Like you don't really have to look at anything, right?
Okay.
For when it is not Hermitian, you basically take lambda 1, and then you, in all cases, you take E1 to En, like to n E1 to En minus 1, is it? And then try to find the error of this projection or something.
What you're asking, that if you're having upper triangular matrices, then
no, like if we have to do the upper triangularization, right?
Yeah,
just the general case, right? Yeah. So in that case, to find U, to find this A, right? We have to take that lambda 1, and then inside U, you first take the eigenvector corresponding to lambda 1, and then I did not really get that. Like, what is the thing? Like, you take the basic vectors, that is the unitary vectors, that is 0. For example, if you get a eigenvalue, then you take 0, 1, 0, 0, 0, 1, and so on. And then you try to project it onto the eigenvector that you got, and then you take the error, is it?
Yeah.
And then, like, I did not understand the step after that. Like, what is within A, you take that B portion error, right? Like the bottom right portion.
Okay. So what he told, I guess, whatever I can remember is like, I've not seen the lecture, but what he told, like, see, for okay, so for example, you have taken 6 cross 6 or 3 cross 3 matrices. Okay, so for 3 cross 3, so the upper thing, what was that? So in the upper thing, whatever the number it has come in, it doesn't matter. In the lower thing, you should get 0, right? This is what slow.
Yeah.
Okay, and then in the lower, see what he told. For example, if you are proofing for the 3 cross 3 matrices, so you'll get in the end 2 cross 2 will be remaining, and then again you have to do the same thing for the 2 cross 2 matrices. This is what I guess the professor has told in the lecture.
And so if it is a bigger one, we just go on for a square matrix, like one size less than the original one.
Okay,
so if it is like,
yeah.
if it is like 6 by 6,
then it will become very difficult. Very difficult to see.
But like hypothetically, like if it is 6 by 6, we take the first one, and then we go for a 5 by 5, and then we go on down.
Then you have to go on.
Okay. Okay. Yeah. Right.
Somebody is asking any trick for calculating A4 which has been so A4 A4 like that was not like we have asked A4 because we have already given the diagonalized form, but like the A you already know that D is very much similar to this A, right? So the intuition behind asking this question was to calculate the eigenvalues of D and DA4 of that diagonal matrices, like diagonal element, and then write 1, 2, like 1 and 6 was there. So you have to calculate I1, 4 and 6, 4. And then you have to do the summation. But mistakenly, like during the review, nobody is like, I only had this question, okay. But during the review, I guess I didn't got any review from anyone regarding, so mistakenly I wrote, I guess the sum of the element, because I don't want to give that in a option form, like, so that's why I just want to convert that in a NAD form. So mistakenly I wrote the element, all the summation of all the element of A. Okay, so that was my mistake only. Okay, so the intuition, like this was not difficult. All the question, whatever I said in the like quiz one, so nothing was like, I guess, difficult to in the perspective of calculation part, right? So A4 you can calculate. So my intuition was not to give you some question where you have to calculate A4. Okay, my intuition was to so that you understand that that this A and D are similar, and you can A and D is similar means the eigenvector eigenvalue corresponding to A will be similar to that of D. Okay, so that was my intuition, but mistakenly I wrote something else, and many of you have struggled to solve that, or if you have written 1 to 97 also, will provide you the marks, and even somebody has written 2 also. I know for 2 you would have got like you would have stuck in that, and you would have like taken more time, but it's fine. That was our mistake, and then so we are accepting that. Okay, we'll give the marks to both. This is what we were asking. I guess somebody was asking. Talam, is it? I guess.
Yes, sir. Yes, sir. Done, sir. Clarified.
Yeah. So okay. So graded, everyone has solved, right? So graded. How many of you have submitted this? Or I guess nowadays, how many of you have submitted this? Okay, Ajit Kumar has submitted. Okay, fine. So okay. Okay, Priyanka also submitted. Fine, good. So he's asking question number 11. So what is the issue in this? Ajit Kumar, can you unmute yourself?
Concept, I don't understand. I am confused in concept.
Okay, so D you have calculated, right? So I'll just write the answer. So you have calculated the eigenvalues, right?
Okay.
1 and 4. Okay, so eigenvalue, whatever you have calculated corresponding to eigenvalue 1, you can calculate the eigenvector, right?
Okay.
So this is the eigenvector, and whatever the eigenvector you'll calculate, just do the normalization. Normalization means you have to divide it with the length of the vector. Okay?
Okay.
Square root of the length of the vector. Similarly, corresponding to the eigenvector, eigenvalue 4, you have to calculate the eigenvector. And this is this column generally represents the eigenvector corresponding to the eigenvalue 4. So whatever you are writing, if you are writing 4 here, you have to write this eigenvector here. And if you are writing 1 here, so you have to write this column here. Got my point? So you
Yes,
can
sir.
just try with that. So we have already in the starting, we have solved. For 2 cross 2, it's pretty simple to solve to get the eigenvector. If this is 3 cross 3, then you have to use you have to use that. Maybe you have read in 3rd or 4th week. You have to use that you have to reduce the last row, and then you have to reduce the other. So you have to make the upper triangular matrices, and then you have to solve for the 3 cross 3 matrices. But here you can do directly. Okay.
Okay.
Yeah.
So what if, when it is in 3 cos 3, for each lambda vector, each eigenvalue, I have to find the corresponding eigenvector. But then I need to take that in the corresponding 3-dimension space, and we have to create the basis vector of another u and v, right?
Yeah.
To do that, from the single vector to expand to these 3, what is the process? Means that I believe a lengthy process. Do you have any shorter method?
Lengthy process only. No, it's like the proof and all in linear algebra is a bit difficult, man. Seriously, it's too difficult to understand also. There is some method, I don't know what is that gram. Some method is there to solve that also. I don't know how generally we solve this. So maybe you can go through that. One good book is there, Gilbert, I guess. That if you go through that, I guess space. I also like, I didn't read full book, but I also go through when I have to take the session and all. So there is a one book, I guess you can. I guess you would be having this book, right? This Gilbert.
Yes, I am having, sir.
So you can go through that, or you can go through the lectures by the Gilbert, I guess. One lecture, but that proof also has not been done there. But I don't know this proof. So I don't know in this book it's there or not. So, but it's better, see, one that professor will take one session. So you can ask that question in that session. Okay, Professor Prasant will take the session, I guess.
Okay, sir. And so one more thing.
Or else we can try to discuss that, but that thing we can discuss it separately. If you contact me on the mail ID, we can discuss in some Gmail or some Gmeet or we'll say.
So can I have your email ID, sir?
I'll just write it on the chat box. Okay, so maybe we can discuss it there. That will not go like live and all. So I'll just write it here itself. So.
And sir, okay.
Oh, sorry. I have to write it here. Okay, I just wrote it here. So you can just copy it. If somebody is having an issue, you can just ask me. Okay. So you can just message me there. I generally reply every mail. Okay. So we can discuss it there.
And sir, do we have many geometrical representation of all these things?
In PC, I'll show you, but I don't know in this SVD. I don't think so. We have any geometrical intuition sort of like GeoGebra. We have not used, I guess, in SVD. In PC, I have something to show, but in GeoGebra, earlier the GeoGebra, whoever was taking like this session, has moved to deep learning. So I think so. He has not made any presentation related to GeoGebra. Okay. So you can go through one, I guess. Do you know that Professor Mitesh Thapar? Like, okay, Mitesh. There are somebody from us only has posted on the discourse, but that also doesn't have the SVD part, I guess. Okay, just try to like I'll try to see if anything can happen in that. Okay, so you want to have the intuition for what? SVD, right? SVD, you'll see that. See how generally in the PC generally we all use all the concept of the SVD. Okay, so maybe that will help there.
And also I try to have a feel. So far in the week 5, we have deal with this complex unitary matrix, all this thing.
Complex thing is very difficult to visualize also. See, for example,
that is there. That is there. But if there is some geometrical interpretation is there, then
okay. So do you have anything like, have you went through this tutorial part?
Which tutorial?
So there is one tutorial in 5th week. Maybe you can go through that.
Acha. Okay.
Yeah.
There is any geometrical?
I guess there is, like Arun did that. I guess there is something. the 5th week and also in the 6th week. So you please go through, and every time you should go through the what you can say, the tutorial part, because the tutorial part is good, I guess. So you'll like the tutorial for 5th week and 6th week. Okay.
Okay, sir.
So maybe that will help you a lot. So I have
Tomorrow's session you will take?
Yeah, I'll be there. One more thing. So I have some question that you can try to solve. That where is that? So there are some basic questions. So maybe you can just go through. I'll just go through in the 10-15 minutes. So okay, so calculate the length. So this is pretty simple. How to calculate the length? Everybody knows, right? So can you speak out the length of this complex vector?
This 1 plus 1, 2, 2 plus 2, 4, 5, sir, root 5.
Yeah, so root 5. Everybody else has done that. So yeah, I'll go through that. The mom is asking you regarding the activity. I'll go through the activity part also. That will not take more than 10 to 15 minutes. I'll go through that. So this, the length is like pretty simple. We can calculate. This is root of 5, I guess. Okay. So can you tell me the length of the complex vector and its conjugate remains same or not?
Yes,
the length
sir.
of the complex vector and its conjugate remains same or not?
It remains the same.
Same, sir.
Why same?
Because
it
only
is the reflection about the axis, right? It is the same.
Yeah. So we are calculating a length also, and it's a reflection only, right? So the length will not change after the reflection, right?
Yes.
So if you are scaling this vector by a complex number, what would be the length of this vector if you are scaling this vector with a complex number? So how will you solve this? Like, can somebody tell me the approach, how to solve this?
So we can take that common, right?
We can take the?
Because it would be like, I mean, if we are like the straightforward way would be like multiplying 4 plus 3i with each element and then like take the
That is the
conjugate.
one method. Yeah, that is the one method.
The other would be like we take if we take one of them as A and the other as B, like if 4 plus 3a is B, it would be AB dot AB for each, right? So,
Okay, that also you can do, or directly you can multiply this, take the mod of both NU. That also is doable, right? Because we have to calculate the length one.
yeah.
Right. So you can directly do this, like mod of NU you can do, right? So the mod of N would be what, 5, I guess, and 5 into 2.25. So you can get directly 11.15. Have you got the point? Like you can do directly also, because you have to calculate the length here. So you are just scaling with the complex number. This also is doable, or else you can do with the basic approach. How generally you did, I guess, that.
Actually,
basic.
I was talking about that second part, that square root thing. That instead of AB, you put new U.
this, sir, can we interpret in this way? Because this 4 plus 3i is basically one point in the complex domain, right?
Correct.
To reach that point in the real axis, I move 4 points, and the imaginary axis, I move 3 points to reach that point. So in that complex plane, we have this dimension, means distance that we have 5. Now I am basically scaling my other plane, that's 1 plus I, 1 minus I, and 1 into that scalar.
Yeah,
and
correct.
accordingly I will again calculate the scaled version of this 3 dimension, again real and axis, to get the distance.
Yeah, correct. So the same thing, like you are doing the scaling of 5 to the complex vector, whatever you have. So this one, then we have. Okay, so check whether these are orthogonal. How generally we check the orthogonality of two matrices, or not matrices, or matrices also is fine, but how generally we take the calculate the see the orthogonality of two column vector.
Product will be 0.
Yeah, so product of two column vectors should be 0. This is not 0, I guess. Yeah. This is 1.
0, 0.
Okay.
Minus
This
1,
is
0.
okay. Yeah. So this is 0. Yeah, correct. Okay. Can you calculate the unit vector that is generally in the opposite of this vector? So unit vector that should be pointing in the opposite direction of this vector. So I'm talking about the unit vectors. You have to divide with. You have to generally normalize this vector. And how we generally get the opposite direction of this vector? If you are having some vector.
So
okay.
we take the negative of the whole thing.
Yeah, so you have to take the like reflection in the point 0, 0,
About,
right?
Yeah, about those. Yes.
Yeah, so, or you can say the 45 degree of that point. So if you will multiply this total matrix, this vector with -1, and then divide it with the what you can say, the if you normalize and then multiply with the -1, you'll get the unit vector in the opposite direction of this vector. Okay. Okay. So tell me whether this is a Hermitian or not. And also tell why is it Hermitian, or if it is not, why it is not.
What is cos pi, sir? -1, right?
Cos 0 is 1.
Cos pi is minus. So
yeah.
It is Hermitian.
Yes, sir.
It is Hermitian.
Yes.
Okay, yeah. But this is -7. How come this -7?
Yeah, that is a real part, right?
Real part.
The conjugate will still remain the same.
Yeah, you got the point. Okay, fine. This one?
This one also.
Yes, it is. It is Hermitian.
Because this minus and iota into iota is 1 and this. Okay. So everybody else is going to that, right? This is the C, the C matrices.
That is not Hermitian. It is not Hermitian.
C into C transpose is Hermitian or not?
C into C transpose.
Okay, and one more thing, can we generalize this? I need to check whether we can generalize it. So it's first calculate first this C, and then can we generalize this C into C transpose?
This we need to calculate and then only able to.
Okay. Okay. Can we generalize this if we are having some square matrices? Okay. Some square matrices, and this is not Hermitian also. If you multiply with the conjugate transpose of the same matrix, then every time it will come Hermitian or not, that we need to check. Okay.
Okay.
Can somebody comment on this? C transpose and C transpose C. For this matrices, if we'll calculate for this matrices, what is this? is minus 2, 1 minus 2i, 0, 3. Minus 2, 1 minus 2i, 0, 3. What you will get?
Sir, 1 plus 2i.
1.
No. In the second one, minus 2, 0, 1 plus 2i. Right?
Oh, yeah. If you multiply, you'll get 4 plus 1 plus 4, right?
Yes.
And then you'll get 3, 1 minus 2i. And then you'll get 3, 1 plus 2i. So I guess every time it will happen, I guess. That is why it's happening here. Right. So I guess this will happen every time.
So for any square matrix,
For any square matrices, C transpose C, because we are getting for these matrices, right?
but is there a condition like should the leading diagonals be real in all cases?
Because if we'll take some real values, if we'll take, I guess maybe there will be some properties. I'm not able to recall the properties. Like if I'm having some real phi. Okay, because see, if we'll take some random numbers, it's not possible that every time if you are taking the transpose and calculating. So, okay, just tell me one matrices, 2 cross 2 matrices. I'll just transpose that and then calculate whether it's coming to be a symmetric or not. So 1, 2, 3, 4. I'll take the transpose of this 3, 4. So if you'll calculate how much you're getting, 1 into 1 and 2 into 2 is 5, right? And 1 into 3 is 3 and 2 into 8 is 11. You'll calculate 3, so you'll get 11 only, right?
Yes.
But this will get different. But that doesn't matter. Okay, so you are getting a symmetric matrix only.
Okay.
So every time it will happen, I guess. Yeah, it will happen every time because we have to calculate the transpose. When we'll calculate the transpose, this column generally is coming to be the same as this one, because here we are doing, we are multiplying this value with this, and here also we are doing the same thing. We are multiplying because after transposing it, the column generally becomes a row of one column, one matrices, and the rows become the column for other matrices. So when we are doing the multiplication, we are getting the symmetric values. Right. So I guess this is correct for every time. This is correct. So every diagonal matrix is a Hermitian matrix.
Yes.
Every diagonal matrices. I'm not talking about the real or complex.
No.
Yes, it is Hermitian. Yes,
Every diagonal cannot be Hermitian.
No, diagonal means the others are 0, right?
Others are 0, but diagonal can be complex and real, right?
Yes. Okay, it has to be real. Yeah.
So the diagonal matrix, if somebody is written every like complex, okay, so every complex diagonal, so the complex number can't come at the diagonal matrices, right? The diagonal element.
Yes.
Fine.
Yes, sir.
I guess the next question is, this is the next one. Every real diagonal matrix is Hermitian. That is true.
Yes. Yeah, that is correct.
Yeah. So this and all we'll discuss tomorrow, because those and all will take the concept of SVD also. So I'll discuss tomorrow. I'll go through activity question also in just 5 to 10 minutes, because somebody was asking regarding that. We'll just go through one.
So before you go that the portion that you just said, the product of two square matrix, that is symmetric only in the case of real, right? When it comes to complex, it becomes Hermitian, right?
Yeah,
Instead of symmetric, it becomes Hermitian.
Hermitian, yeah, fine. So for whenever there is a normal like real number, it will become, because in the SPD also we use the same concept, right? In the SPD also we do the same thing. Like if I'm having a rectangular matrices of 2 cross 3 and then 3 cross 2, that we have to diagonalize. So this A is there, so this is A transpose. So it'll come with a symmetric matrices that will be 2 cross 2, right?
Yes.
Yeah. So because if we are having a large number of data set, like for example 1,000 features, and then we are having 1 million of data set. So generally, how generally we use this SVD concept to visualize those 1,000, what you can say, the data, what is that, the features and all. Generally we use this concept in the SPD. Yes. So we generally calculate, and for the real symmetric matrices only we can do a large bunch of things. Okay, so that is how I guess A and A transpose get converted into a symmetric matrices, and then from this symmetric matrices we can use the concept of SPD and we can split this matrices, okay, or diagonalize this matrices to get a diagonal matrix, matrix to have a symmetric matrices. Okay. This I'll discuss more. Then we have, okay, so the first statement is like the statement that inner product of the two matrices always common is false statement, because if you'll calculate the xy and yx, you'll get the conjugate of both, like conjugate of the first one. Okay, which are the following: compute the square of the length of the x1 and x2, and x1 is real, so doesn't matter with the x1, only you have to check the x2. Okay, because x2 is a complex number, so you have to check for the x2 only, because x1, the transpose or the conjugate, whatever you want to do, it will be same. Not the transpose, the conjugate will be same. So you just have to check for the x2. Okay. Then given that the complex A, or is this like A star is what? Conjugate of the transpose. Which of the following is true. So this also has been discussed in the lecture itself. So you can, so this is correct, I guess. Not the first one, the second one is correct. The fourth one is correct. This also the properties have been discussed in the lecture itself. So the conjugate transpose of any matrix, you already know how to calculate the conjugate transpose. Okay. The Hermitian matrix in the vector are generalization of what? The Hermitian matrices in a complex vector space are generalization of what?
Symmetric
matrix in a, yeah. Okay. Hermitian matrices are orthogonally diagonalizable. Orthogonally diagonalizable. This is orthogonal diagonalizable or unitarily diagonalizable? This is the Hermitian matrix generally we can diagonalize unitarily, right?
Unitarily, yeah.
And the diagonal element of the matrices, Hermitian matrices, are, yeah, this is true. And this is true for all the matrices, Hermitian matrices. It's not for some. The eigenvalues should be real, because the eigenvalue for the real of the eigenvalues for any of the symmetric matrices, or you can say the Hermitian matrices, would be a real one. So every time you'll get the real value. So eigenvector corresponding to distinct, or yeah, this is true.
Yeah, sir,
Yeah.
in the case of Hermitian matrices, like so if we have a repetitive eigenvalue, then it will become upper triangular.
Repetitive, okay, yeah. So you'll not, so what happens in the repetitive, you are asking regarding the eigenvector, right?
Yeah. No,
So,
repetitive eigenvalue.
Okay,
Let's
so
say if we have like lambda into lambda minus 2 square or something like that.
Okay, so you got the eigenvalue as something like 1, 1, 2.
Yeah.
So this is repetitive. So see, in these cases, you can get the eigenvector, 3 independent eigenvector also you can get. Like for example, you know that identity matrix, right? Identity matrix generally have the eigenvector as eigenvalue as 1.
Yeah.
But it will be having 3 independent eigenvector. So one thing is, if you are getting n distinct eigenvalues, so that is pakka you'll get 3 distinct or 3 orthogonal that eigenvector. But if you are having a repetitive one, then you have to check whether the multiplicity generally you need to check. That I guess has not been taught. So you have to check the geometric multiplicity and arithmetic multiplicity for those cases. And if that is same, then you can say you'll be having a different eigen, like all the three three independent eigenvector. Otherwise, you'll get a you'll not get a three independent. You'll get a less eigenvectors. That maybe you can refer some other books also regarding GM and AM. Okay. Geometric multiplicity and arithmetic multiplicity to get a brief idea regarding when, if like for example, everybody knows that if you are having n distinct eigenvector, like if you are having a matrix of 3 cross 3 and if you are getting 3 distinct eigenvalues, so you'll get 3 different, like 3 orthogonal eigenvectors. Okay, but if you are having 3 independent eigenvectors, but if you are having a matrices of 3 cross 3 and you are getting 1 1 2 or some repetition is there, okay, that so in those cases you can't directly say whether all the eigenvectors are independent or not independent. In those cases, you need to check the GM and AM. One thing. That's why generally, whenever you go through the eigenvector, they'll say you the sufficient number of eigenvectors should be there. What is the sufficient number? That nobody knows. Like you have to check with the geometric multiplicity or arithmetic multiplicity. That you can refer. Somebody has posted in the discourse of the Professor Mitesh Thapar. Yeah, Mitesh Thapar. You can go through his lecture. Not lecture. He's just go through his slide in the starting 4 or 5 slides only. You'll get to know regarding the AMG. Okay.
Okay.
And then we'll move to the third part. And the third is also, so this is the basic properties of unitary, when the matrix is unitary or not unitary. So these are all simple. So you'll just, if you are going through the lectures also, they are pretty simple ones. Don't have to use your brain also to solve this problem. Okay. So diagonalization also, I guess. So there is only 2 questions, and that is for a matrices. We can find the dash matrices so that where the A is the diagonal matrices with the, so the A should be Hermitian and then B should be a unitary matrix. That's why generally say the A matrix is Hermitian and you have to diagonalize that matrices, you'll get a unitarily diagonalizable. Okay, so that is the thing. And so as for the spectral theorem, okay, this is also simple if you are just going through the lecture. So the 4th, 5th lecture is not that useful, but okay, the proof is not that useful, but you should be aware of the how generally you diagonalize and how generally you diagonalize the Hermitian matrix to get the unitary matrix. Okay, so you should be aware of that. Whenever you are having a real symmetric matrices, how generally you diagonalize. If you are having the Hermitian matrices, how generally diagonalize and what are the end product. And if you are having the basic thing starts from the similarity of the matrices, like the spectral theorem. If you are having 2 symmetric matrices like A and B, and if you are able to write this B in the form of P inverse A, P, and P is that matrices that you get from the eigenvectors. Okay, so the A and B will be a symmetric, like not symmetric, the similar matrices. Similar matrices means the eigenvalues will be similar. Okay. So this is the most important thing. Otherwise, the proofs and all, you can go through that if you are able to grasp. Otherwise, you can skip it also because nobody is going to ask you the proofs and all. Okay, you should be much aware of that. See, in the next, like in PC and all also, or you will go to the other courses also. Only you should be aware of the linear algebra part is important. Okay, in the PC also, I'm telling you the principal component analysis. Generally, we used to have a very big proof. Okay, but if you write the code, it's a simple, what do you say, simple code of PCA. You can use directly and it will calculate everything. Whatever, like with a Python also you can do, like you can write all the code of the PCA, okay, in the data set. But in SQL, you have already a PCA basic library that you can use directly. Okay, but the thing is, you should be aware of why we are doing the PCA, why are we doing SPD. Many a times, companies generally ask, what are the mathematics behind the PCA we are doing? How generally the PCA works? Okay, that is, if you are aware of how does it works, we can use those library in a nicer way. This is the one thing. Okay, many a times I also do forgotten many of the maths behind many of the things. Okay, but the basic things I have a bit knowledge regarding how generally, like what are the maths behind the most of the things we are using in ML techniques. Like if you are using the logistic regression or the random forest or the any of the gradient descent. So what are the math behind that? How does it work? That you should be aware of that. And that's it. I not the proofs and all. Like you're not going to be a. If you are going to be a researcher, okay, you have to do. But if you are not, if you're just going to get like a good command in the MLM, so you should be aware of basic maths behind all the algorithm. That's it. So this is also the fifth. Also is like this is the theorem that's used to prove the Hermitian matrices. It comes from the spectral theorem only. The spectral theorem is the most important. So everything comes from the spectral only. Okay. So these are pretty simple one. And the practice assignment we already solved. If you are having any issue in the graded, who have not submitted, you can ask. But if you will not solve the equation, I'll tell you the method just to solve that. Otherwise, the fifth week, the most important things are going to come. Like the most difficult part is going to come tomorrow, I guess, the SVD. That will be having a bit difficulty in understanding. Other than that, I guess everything will go smooth after the SVD and PCA. Everything is smooth. Optimization will start. You will not feel any issue. You will not need us also in the optimization. After the 7th week, you'll not need anyone. You'll just go to the video and you'll able to grasp everything. Okay. So
this might be a silly question, but in the case of this diagonalization, this unitary diagonalization, right?
Yeah.
That is, so the same thing as in symmetric diagonalization can be done. For example, if we have matrix A,
can be done, but not as a that. If you are having a symmetric matrix, compulsorily it will not be a unitarily diagonalizable. It will be orthogonal diagonalizable, but not the unitarily diagonalizable. So for some matrices or for some symmetric matrices, it can come, but not for all. But if you are having a Hermitian, then pakka it will come as a unitarily. You can diagonalize in unitarily form. Okay. But if you are having a symmetric, you can definitely the diagonalized form will come in the form of orthogonal, but not in the unitarily like that. That matrix is not must be unitarily diagonalizable. Have you got the like point?
Yes.
Yeah.
But like for any matrix, we can have the upper triangularization will happen for any matrix, right?
Yeah. That will happen for any matrix. That is the Score theorem. Yeah.
And so we can use the same thing we did for the symmetric when we was orthogonally diagonal. So for example, we have A is equal to U star U lambda A star, that A raised to, like we did in the exam, A raised to 4. We just need to take the
that
power
you can
of
do everywhere. Yeah, that this is why we are doing this. This is why we just have to get some diagonalized. Why we are doing diagonalized? We are just transforming that matrix to a similar matrix that consists of the important things like the eigenvector, eigenvalue of that matrices. That is why we are doing the diagonalization to get a simpler matrices that if you operate something on A and if you are operating same thing on D, that give us the same aspect. That is why we are doing the diagonalization.
Okay.
So I guess we'll meet tomorrow again. I guess the timing and all will be updated by evening by 6 the calendar in the calendar. Okay. So we'll meet tomorrow again for that next 6th week. So you can complete the 5th week and submit it today itself. If you're having any issue, you can just mail me or post it in the Discord. You can tag me also. This is Vishal, okay. And you can tag me and then I'll try to solve there. And complete the reflection thing also. It's a pretty, it's like 2-3 question, I guess. That is simple one. So just try to submit it today itself. And then we'll start the 6th week because we are already late. And regarding the extension also, I already like till now didn't get the, yeah, I'll check the message once again. Okay, I didn't got any message till now. Okay,
regarding the deadlines?
Yeah, the extension of the 7th week. Sorry, 6th week. Okay, so I didn't got till now any message. Yeah, so I'll inform you that also will inform you tomorrow. So tomorrow I'll inform you whether we are extending or not. Okay. I'll just message again, I'll ask regarding the extension, and tomorrow we'll confirm that. So till that time, you can complete this 5th week, and we'll start with the 6th week tomorrow. We'll discuss this SVD and the basic properties of the positive definitors. So with the help of matrices, we'll be able to see whether the matrices are definite or not definite or indefinite or not. So we'll see tomorrow, and then maybe I guess one more session will be there in this week, so that we'll try to solve like the graded assignment, or we'll try to solve some questions from the 6th week. Okay.
Okay, sir.
Okay. So thank you everyone for this
Thank you,
session,
sir.
attending this session. Okay.
Thank you, sir.
Thank you, sir.
Yeah, thank you. Thanks everyone.